Hello engineers and welcome back to Civil Nirman. So in part 1 we learned what the GL parameter is and why it's essential when seismic forces affects the portion of the structure below ground. Now it's time to validate the results using both manual calculation and the STAAD model. So let's verify if STAAD respects the code's treatment of seismic base shear distribution below and above ground. So let's just understand the STAAD model setup how I have done. See, this is the simplified structure we have created in STAAD. Basically, it's a 3D frame with the multiple levels, including underground levels, which are extending down to minus 20 feet. So here, GL is set at y is equals to minus 2 feet as per the following syntax which you can implement in your STAAD model. So the syntax will appear over here. So the seismic zone factor, response reduction factor and important factors are defined, but the game changer point is GL. GL minus 2, this tells that the ground level is at y minus 2 feet. Now in the next phase, you just have to go with the load assignment and joint weight. So basically we have assigned joint weight of 100 kilopascal to all the relevant nodes from level minus 10 feet up to the roof level covering underground and superstructure mass. Now to represent this, how it will look in the STAAD editor, you can check this particular syntax. Further, I'll show you how I have modeled this particular sample problem in the STAAD. But to give you the overall introduction summary, here I have specified this. Now see, this covers both above ground portion, that is minus 2 feet, and below ground portion, which is minus 2 feet. Now let's validate if STAAD splits the base shear as per code. Also, I am going to show you whole manual calculation which I have covered in this session.
So let's understand how we can go for the manual calculation check. STAAD.Pro tells you the base shear, but how do you know it's right? So in this video, we will manually verify the base shear for the multi-story steel structure using this IS 1893-2016 and compare it directly with the STAAD output and manual validation. Right now, see here you can observe one structure, a 10-story steel moment resisting frame, which I have considered in the modeling. Right, it has 0 to 100 feet height, 10 feet spacing, a W10 member section. It has fixed supports, and we have implemented joint weight of 100 kilopascal per joint. Following are the design parameters you can observe over here, which are considered for the seismic definition part. Now, to avoid the larger length of the tutorial, I have already modeled, but over here I'll going to show you how I have considered each parameter with the manual calculation validation. So here you can observe all the inputs which are utilized in your seismic definition, right? Time period, zone factor, importance factor, response reduction factor, soil type, structure type, ground level consideration and the building height. Also, you can check that for this particular 10-story building, this level is at 00 coordinate, and at minus 20 feet down we have this fixed base, and we have considered ground level somewhere here, so from 00 coordinate at minus 2 level. And the similar replication I have considered in the STAAD model. So let's switch to the STAAD model part. Here you can observe the complete model over here. I have identified all the segments with the spacing in each direction. You can check this model. Right, for the loading part, if I'll show you, we have this seismic definition part available over here, and the load case detail in X, Y and Z direction. Right, I have created 3 cases for all 3 direction, and you can observe that I have added a joint weight of 100 kilopascal. You can click on the definition part, based on the parameters which I have shown you. All the parameters are implemented over here to generate the seismic definition. So here one important part, see the seismic zone factor, response reduction factor and important factors are defined, but the game changer portion is your GL minus 2. Now this tells that the ground level is at y is equals to minus 2 feet, right? And see, we have assigned the joint weights of 100 kilopascal to all these relevant nodes from level Y, from minus 10 feet up to the roof level, from here to all till top. So basically it covers the both above ground. So basically it covers both the segments, right? Above ground portion, which is greater than minus 2 feet, and below ground portion minus 2 feet, right? So now let's validate if STAAD splits this base shear as per code. So I'll give you a brief on this. So first of all, what we're gonna do is that, see, we have seen over here that ground load is at minus 2 feet and floors below ground are minus 10 feet, right, and minus 20 feet, this too. Okay, so we will use AH for above ground and use interpolated AH or 0.5 AH for levels below 30 meter. Okay, now we will go to the STAAD model and run this analysis. So basically I'll run this analysis. You can create this model quickly. It will not take much time. One important thing I forgot to tell you that I have added this perform analysis sprint load data in the editor file. Okay, I'll just quickly show you over here. So you have to add this perform analysis sprint load data syntax over here. Okay, so it will help us to identify the load details further in your output. So I'll click on the output over here. Right, and you can check out this. For each direction it has specified all the parameters with calculations, and the base shear summary is also specified for the above ground and below ground as well. Okay, so first thing you need to do after run analysis is check if the base shear values are different for upper and lower floors. Cross verify each joint's lateral force in X and Z direction. You can use these result tables and compare them line by line with the manual calculation, which we're gonna check out further. See, we have with each floor values available over here. Similarly for below ground level, we have all the values, base and mass shear summary, base and time period summary too. Let me just give you an example. Let's say, for example, joint at y is equals to 10 feet. It should match your qy is equals to ah into wy. Similarly, joint at y minus 10 feet should match qy is equals to interpolated ah into wy, and joint at y minus 20 feet should match your qy is equals to 0.5 ah into wi. Now if everything aligns, your GL parameter is working perfectly, right? So now let's switch to the manual calculation part quickly. So first of all, I'll go for the sample calculation of AH for 30 meter height, right? Based on the parameters, every parameter is specified over here. And I have already tabulated all the results value over here. So let me just give you a verification for one of each parameter. So I'll give you one sample calculation, rest of the things you have to calculate by your own. Okay, so just for your understanding, so we will start with the AH, Z by 2, I by R, SA by G value. So all the parameters I have already shown. You can put the Z value, I by R value, and SA by G values over here. Okay, so after this, if I calculate the AH value, I'll get the value as 0.00 0.02664, which is for normal building height. Okay, now for 30-meter height limit, we will reduce this SA by G based on our time period T at 30 meter. Okay, which will typically results in your lower SA by G value. So if I assume for 30-meter height T is equals to 0.5 second, okay, so from spectral charts you can compute this SA by G value as 0.453, and again if I compute the AH value based on this 0.16 by 2, 1 by 2 and this SA by G value, I'll get the exact value of 0.01209 over here for 30 meter, which is matching. Similarly, you can calculate it for the Z and Y as well. Let me show you for the Y direction as well. So I have calculated this particular for the Y direction as well, and you can see my answer is exactly matching over here. The calculation is in front of you. It's super simple. You just need to enter the parameters. Similarly, let's go for the design horizontal acceleration coefficient sample calculation. So for the horizontal acceleration as well, we have the following parameters: T value, SA by G value, Z, I and R. I'll put the value for AH over here, and you can compute this AH as well as 0.907. And further, if you put this value as 0.907, you will get AH value as 0.02418, which you can check over here. Okay, so this is horizontal acceleration coefficient 2018. So code requires this a reduced base shear for the flexible structures over 30-meter height. So let's apply that now. So let's say for the X direction I am considering, so I'll consider the reduced AH value based on this equation, and I'll put the values over here. I have already calculated AH. You just have to put your values over here for the reduced consideration, and here you go, 0.02197. So this is your reduced AH or AV value, right? Similarly, you can calculate for the Z and Y direction as well. So I'll leave it on you. Tell me in the comment box what will be value. Already I have put this results over here. You can match your values by manual calculation for X and Z as well. Now let's talk about the vertical distribution of forces above ground level. Now during graduation, you already have learned this particular calculation by calculating a base shear calculation for the sample frames, right? In graduation, in the earthquake analysis, we have the same calculation. So the same calculation is provided over here in the tabulated form. Now for your understanding, each floor is specified over here with the WI and HI value and the equation that you have to follow. So I'll provide you one sample calculation of these 100 feet. Okay, let's understand this. So for floor 100 feet, we have this 400 HI value and WHI square value. I'll consider the distribution factor from this equation. So I'm getting this as 0.3074. You just need to divide this, right, based on this equation. WHI square divided by summation of this. So this we have put in the equation form. That's it. Okay, so we will get the base shear value here VB as 87.064, right? And based on this, you just have to multiply your VBAH into W, right? So we will get the value of 26.761, which is exactly matching over here. Similarly, you can calculate it for the Y direction, 49.179. Now let's understand the vertical distribution of forces below ground level. So this one is the additional segment I can give you. Same way you have to calculate the distribution factor. I have calculated this. You have to calculate again. You have to look for your VB value that you have computed and calculate your QX and QZ for the X and Z or Y direction. Similarly, for each level, Entire calculation is specified over here. You can check floor wise and compute your value and compare your results. So I hope this video helps you out. I have posted all the results over here for 100, 90, 80 and each floor. Check your calculation and match it with the manual calculation. I hope this video helps you out. Stay tuned for all the updates in structural engineering, and always remember, don't blindly learn softwares, learn concepts. Thank you.